The core of the Sun is considered to extend from the center to about 0.2 to 0.25 of solar radius. It is the hottest part of the Sun and of the Solar System. It has a density of 150 grams per cc at the center, and a temperature of 15 million degrees Celsius. The core is made of hot, dense gas in the plasmic state, at a pressure estimated at 265 billion bars at the center. The core inside 0.20 of the solar radius contains 34% of the Sun's mass, but only 0.8% of the Sun's volume. Inside 0.24 solar radius, the core generates 99% of the fusion power of the Sun. There are two distinct reactions in which 4 hydrogen nuclei may eventually result in one helium nucleus. The proton-proton chain reaction, which is responsible for most of the Sun's released energy, and the CNO cycle. Equilibrium. The rate of nuclear fusion depends strongly on density. Therefore, the fusion rate in the core is in a self-correcting equilibrium. A slightly higher rate of fusion would cause the core to heat up more and expand slightly against the weight of the outer layers. This would reduce the fusion rate and correct the perturbation, and a slightly lower rate would cause the core to cool and shrink slightly, increasing the fusion rate and again reverting it to its present level. However, the Sun gradually becomes hotter during its time on the main sequence, because the helium atoms in the core are heavier than the hydrogen atoms they were fused from. This increases the gravitational pressure on the core, which is resisted by a gradual increase in the rate at which fusion occurs. This process speeds up over time as the core gradually becomes heavier. It is estimated that the Sun has become 30% brighter in the last 4.5 billion years and will continue to increase in brightness by 1% every 100 million years. Energy transfer. The high-energy photons released in fusion reactions take indirect paths to the Sun's surface. According to current models, random scattering from free electrons in the solar radiative zone sets the photon diffusion time scale from the core to the outer edge of the radiative zone at about 170,000 years. Further, they cross into the convective zone, where the dominant transfer process changes to convection, and the speed at which heat moves outward becomes considerably faster. In the process of heat transfer from core to photosphere, each gamma ray in the Sun's core is converted during scattering into several million visible light photons before escaping into space. Neutrinos are also released by the fusion reactions in the core, but unlike photons, they very rarely interact with matter, so almost all are able to escape the Sun immediately. For many years, measurements of the number of neutrinos produced in the Sun were much lower than theories predicted, a problem which was recently resolved through a better understanding of neutrino oscillation.